Hi, I'm Eddie Amari, and I'm going to talk about the statistical query complexity of manifold estimation. This is the joint work with Alexander Knapp. This work deals with geometric inference, which basically refers to the understanding of the underlying structures of possibly curved data. Such intrinsically curved data arise naturally in many different areas, such as biochemistry, image analysis, or material science. Generally, you're given a sample x1 to xs that lie on or nearby a submanifold which we denote by M. M is typically of low dimension intrinsically compared to the ambient dimension n. The goal is to estimate M via an estimator M hat that approximates it either geometrically, topologically, or both. Doing so, the learner reduces drastically the dimension and recovers global data information encoded in the topology. Here, the estimation of M will be done in Hausdorff distance, which is a L-infinity distance between compact subset of Rn. This is the most commonly used distance in stats estimation, and it provides strong guarantees in topological data analysis, such as the stability of the so-called persistent homology. Now that we know what it means to estimate M, let's move to the actual class of manifolds we'll look at. The model we consider is composed of C2 smooth d-dimensional submanifolds of Rn that have no boundary. For reasons that will be clear later on, we assume to know some a priori location information about it, encoded in the fact that M is contained in the known ball of radius r. The main regularity assumption is encoded by the reach, which roughly measures how far M is from being convex. In particular, it prevents M from having arbitrarily large curvature and narrow quasi-self intersection as shown on the picture. On top of M, we'll observe data from some distribution D, which with the port M, that is roughly uniform. This model has already widely been studied by computational geometers. For instance, reconstruction can be done in the following way. Assume that the dataset x1 to xs, seen as a point cloud, contains noise of magnitude at most epsilon. It forms a root epsilon covering of M, and that tangent space estimates are available at each data point. Then one can compute a triangulation M hat based on the points that is epsilon close to M in Hausdorff distance and that has the same topology. Here, the quadratic gain from a root epsilon sample to an epsilon approximation comes from the fact that M is of class C2. Now, if the sample is random and without noise, one can show that it covers M with high probability. Furthermore, performing local principal component analysis around each point allows to estimate tangent spaces precisely enough. Plugging in the previous method from computational geometry, we get that with high probability, the associated triangulation has precision epsilon of order log s over s to the 2 over d. Here, let me recall that d is the intrinsic dimension of the manifold and that this result does not depend on the ambient dimension at all. This rate is minimax optimal. Equivalently, given target precision epsilon, the sample complexity for estimating M is of order 1 over epsilon to the d over 2 up to log factors. Note that here, the method relies heavily on the points and suffers from severe instability if substantial noise is added. If ambient uniform clutter noise is added, an iterative pre-filtering of the points allows to filter clutter and then to recover the same sample complexity using the same method as before. Unfortunately, this decluttering method relies on the uniformity of the ambient points and it may fail for other types of noise. Up to now, no method can handle noise in manifold estimation satisfactorily. Among other features, our work overcomes this lack if the clutter distribution Q0 is known. So far, the framework we have considered is that of sample, which is also known as backlearning. In this framework, some oracle who knows the underlying distribution D generates S random variables from D and sends it to the learner. Then, the learner is allowed to compute any estimator theta hat based on this sample. In general, the learner has the a priori information that the true distribution D lies in some model D Cali. they want to estimate some functional theta of d for some metric rho. Given target precision epsilon and the probability of failure alpha, an estimator is said to be valid if it falls epsilon close to theta d with probability at least 1 minus alpha uniformly over the model d. Here, randomness is driven by the randomness of the sample, and the smallest sample size S star for which such an estimator exists is called the sample complexity of the problem. A few examples of statistical problems written this way yield functional theta of d being the mean of d, which is a vector, the density of d with respect to Labag, which is a function, and the support of d, which is a compact and which we focus on in this work. The packed learning framework presents some limitations. For instance, no computational complexity is encoded whatsoever. Also, optimal estimators might be very sensitive to noise and not robust at all. Finally, data is entirely disclosed to the learner, which clearly brings privacy concerns if it's not a trusted party. To overcome these issues, Kearns proposed the so-called statistical query framework, which we will now present. Here, the learner will access the underlying distribution iteratively through the averages of functions that the oracle is allowed to perturb adversarially. More precisely, the learner first asks a bit of information about d via a real valued function, a query R1 from Rn to the interval -1, 1. The oracle then answers any value A1 that is tau close to the true integral of R1 with respect to d. This interactive process continues, and the learner sends R2, which can depend on the previous answer, gets A2, and so on and so forth. The process then stops after a few steps, and the learner computes their estimator theta hat of theta d based on the answers A1 to AQ. Given target precision epsilon and tolerance parameter tau of the oracle, the smallest number of queries Q stars required by an algorithm to output an epsilon precise estimator against all possible adversarial stat tau oracles is called the query complexity of the problem. Adversariality of the oracle effectively forces both data privacy and robustness of the estimators. Note that here no randomness is present a priori, although the oracle and possibly the learner is allowed to randomize its strategy. As a first example, let's discuss the mean estimation problem. Consider the model D-Kali composed of all the Borel probability distributions over the unit ball of Rn. For all distribution d, in this model we want to estimate its mean vector theta d for the distance given by the LP norm. A simple algorithm consists in querying the n coordinate functions. Doing so, the learner gets all the components of the mean vector up to precision tau. Hence, after n queries, this results into a global precision tau in L infinity norm, which is optimal. In L2 norm, the naive strategy I just described only yields precision root n times epsilon with n queries. As shown by Feldman, Guzman, and Vampala, one can actually achieve a dimension-free precision of order tau with only 2 n queries associated to a properly chosen tight frame, and this precision and query complexity are optimal. Coming back to our manifold estimation problem with SQs, we propose a purely geometric query-based algorithm that will use routines to explore n. The idea consists in building greedily a point cloud that will mesh the manifold so that the known deterministic reconstruction method described before can be applied to it. This algorithm, called manifold propagation, is similar to breadth first search. Just for a moment, let's assume that using statistical queries, we're able to locate a point x0 hat close to m. This point will be used as a seed point for the algorithm. Then, assume also that we can cook up a precise enough tangent space estimation routine t hat around x0 hat. It provides us with a local linear approximation of m, so that we're sure to find m nearby a small ball of t hat. Hence, we can consider enough points on a small sphere of t hat and project them using another routine pi hat based on SQs. These projected points are inserted into a queue and the seed point into an output point cloud. Until the queue is empty, pick a point in it and explore its neighborhood in the same manner using the tangent space and projection routines. Then remove the explored point from the queue and add it to the output. To avoid backtracking, do not take into account the candidate tangent points that are too close to the already explored zones. This non-backtracking check does not use the routines and hence no extra statistical query. Here, the projection step is necessary to reboot the process, as otherwise, estimation errors and linearization errors would accumulate at each step. At the end of the day, the manifold propagation algorithm builds a point cloud O with attached tangent space estimates that we expect to approximate M well if the geometric routines x0 hat, t hat, and pi hat are precise enough. This is exactly what we show in this theorem. Under natural geometric assumptions on the routines, we show that the manifold propagation algorithm terminates and outputs a point cloud and linear spaces that yield an epsilon approximation of M after triangulations. Furthermore, it calls the seed point routine only once and the tangent space and projection routines at most 1 over epsilon to the t over 2. As a result, we have reduced quantitatively the query complexity of manifold estimation to the query complexity of 3 simple geometric routines. Let's now explain how we can design them in StatTau. For the projection routine, we stand at a point x0 already known to be lambda close to the manifold, where lambda is small enough. We want to estimate its nearest neighbor, pi m of x0 on M. As we only have access to averages, we leverage the fact that pi m of x0 is close to the local conditional mean of the distribution D around x0. This local conditional mean can be accessed via statistical queries using the mean vector estimation technique from Feldman, Guzman, and Vampala I just mentioned before. At the end of the day, this routine requires O of n queries, and if the localization radius is properly chosen, we show that it outputs an estimated projection that has precision of order lambda squared max tau to the 2 over d plus 1. That is, on one hand, the farther x0 to m, the less precise it gets, and on the other hand, the adversarial tolerance tau yields a best achievable precision of order tau to the 2 over d plus 1. Here, the quadratic dependency lambda squared strongly leverages the fact that M is of class C2. Next, for the tangent space routine, we now stand at an even closer point x0 and we want to estimate the tangent space of M locally around x0. To do so, we perform local principal component analysis, which requires to estimate the local covariance matrix sigma around x0. Sigma can be thought of as a mean vector in dimension n times n, so that we may use the same strategy as before. Estimate it up to error O of tau in Frobenius norm using O of n squared SQs. This would yield a quadratic query complexity in terms of the ambient dimension, which might be very large. Using matrix completion results, one can actually mitigate this dependency to O of nd up to log factors. Indeed, sigma is close to being rank D, so that we only need to estimate its first D largest components. Beyond tangent space estimation, let me mention that a general matrix completion result for SQs can be found in the paper. At the end of the day, this routine requires O of nd queries, and if the localization radius is properly chosen, we show that it outputs a D space that has precision of order root eta max tau to the 1 over d plus 1. Here, the root eta dependency of the precision is what is expected, since estimating a tangent space roughly boils down to estimating a first order derivative. Finally, for the seed point detection, we start with a ball radius r, and we want to locate some x0 hat that is eta close to m in this ball. First, we use a divide and conquer strategy by querying indicator functions of unions of elements of a small grid. At each step, this allows to detect whether they have non-zero mass. Eventually, it provides us with a grid element that intersects M, but as this process does not really use the fact that M is C2, it doesn't have a good precision. Starting from this grid element, we apply iteratively the projection routine pi hat described before to enhance quadratically precision at each step. At the end of the day, this routine requires O of n log of r over eta queries, and if the localization radius is properly chosen, we show that it outputs a seed point that is at distance at most eta max tau to the 2 over d plus 1 from M. Putting everything together, we get the main result of the paper, an upper bound on the statistical query complexity of manifold estimation. Essentially, if epsilon is at least tau to the 2 over d plus 1 and that tau is not too large, then manifold propagation executed with the SQ emulated geometric routines provides a deterministic statistical query algorithm with precision epsilon. It requires at most n times log of 1 over epsilon plus 1 over epsilon to the d over 2 queries to stat tau. The explicit dependency in the parameters of the model is displayed here. Now, given this construction, the natural next question about its optimality is at least twofold. On the information theory side, given tolerance tau, the question is whether we could achieve a better precision epsilon. On the computational side, given such an achievable precision epsilon, we ask whether an algorithm could make significantly less queries. For the informational lower bound, we build two submanifold M0 and M1 that are indistinguishable in stat tau. That is, their associated uniform distribution are tau close in total variation. Simultaneously, we build them so that they are far away by at least tau to the 2 over d plus 1 in Hausdorff distance. This can be achieved by bumping M0 locally as shown here. Since an adversarial oracle can fool the learner and pretend M0 to be M1 and vice versa, the Hausdorff distance between M0 and M1 clearly is a lower bound on the precision of any SQ algorithm, no matter the number of queries it does. Therefore, this gives us the first precision lower bound displayed here. For the computational lower bound, we build many manifolds that are epsilon away from each other. That is, we build the packing of the model for the Hausdorff distance with large cardinality n Cali. Again, this is done explicitly by locally bumping a manifold with large volume. The cardinality n Cali we obtain is given here and matches with the query complexity of our method up to log n factors. Then, we roughly argue that any stat tau oracle is only forced to reveal log of 1 over tau bits of information at each query, since it locates a mean in the interval -1, 1 up to tolerance tau. As an epsilon precise SQ algorithm must at least distinguish between all the n Cali manifolds of the packing, its number of queries clearly must be at least log of n Cali over log of 1 over tau, which yields the displayed result. Note that when the bounding ball radius r goes to infinity, the given complexity blows up, and this shows that if no prior information about the location of M is given, no SQ estimator with finite complexity can succeed. This phenomenon is specific to SQs and does not occur in the sample framework, since the first sample would provide such location information for free. To summarize, this work derives nearly matching upper and lower bounds on the statistical query complexity of manifold estimation in the C2 case. An important direction for future works is extending these results for smoother manifold classes, such as CK for k greater than 3. The slight discrepancy on the achievable precision epsilon given tolerance tau is also left open. That's all for this video. Thank you, and I'm looking forward for your comments and questions during the online session.